Hi everyone, today we'll talk about how homotopy theory is wrong. Let's start with a simple plane and pick a disk on that plane. Now just extrude that disk into a cylinder, so you obtain that shape. Here, the cylinder is empty inside and there's no disk below anymore, just a hole. Now, you might ask yourself what the fundamental group of that space is. It has to be trivial, right? Because if you draw any loop, there's always a way to deform it into the trivial loop. If needed, you might have to move the loop above the cylinder, but that's perfectly fine. But what if I told you that this cylinder was actually really tall? I mean really tall. For this, let alpha be a very large ordinal number. For safety, you can take alpha to be an ordinal of cardinality 2 to the cardinality of the continuum. Now consider the standard closed interval from 0 to 1, and define the concatenation of alpha copies of that interval. We define it, technically, as the Cartesian product of the ordinal alpha with the half-open interval from 0 to 1, equipped with the lexicographic order, to which you adjoin a single point that will be the maximum. Then, you turn that ordered set into a topological space by equipping it with the order topology, that is, the topology generated by its open intervals. The resulting topological space we denote by alpha.01. You may think of this space as the space of all ordinals smaller than alpha, but where you allow ordinals to have decimal places, so you might have things like omega plus 1 over pi. You can visualize this line in the following way. First, visualize the ordinals up to alpha, and then fill in the blanks between the ordinals. In this way, you obtain an extremely long line. You can then construct a long cylinder by taking the Cartesian product of a circle with that very long line. And then you also add a disk on top. Like previously, that cylinder is empty inside, and there's a hole below. Now, if you consider a loop around that very tall cylinder, it might happen that there's no way for a homotopy to deform it into the trivial loop. The reason is that, in some way, homotopies are just too short. Indeed, homotopies, just like paths, are by definition parametrized by the standard interval from 0 to 1. But that interval is too small to deal with spaces of large cardinality, like those constructed using alpha. This is the reason why that space isn't actually simply connected, and this is contrary to our geometric intuition. A funny metaphor to visualize this phenomenon is the following. Imagine that there's a very tall cylinder, with a rubber band wrapped around. Then, maybe you could remove that rubber band using your hands, but the T-Rex may not because its arms are too short to reach the top of the cylinder. From the T-Rex point of view, it's like the top of the cylinder doesn't even exist, as if the cylinder was cut in the middle, and in that case the space you see is basically a circle. So the fundamental group of the path-connected component of the T-Rex is Z, it's non-trivial. As we have seen, it's possible for a space to not actually be simply connected, although our geometric intuition says that it should be. We can ask whether the opposite also happens. Is it possible for a space to look like it's not simply connected, but for all loops to actually be contractible on that space? Well, it turns out that this is actually possible. Consider the following space. It looks like a plain old circle, right? So its fundamental group should be Z. What I haven't told you is that the circle is super big. It's obtained by gluing both ends of the super long line we've seen before. For this reason, we run into a similar problem. Now, it's not the homotopies this time, it's the loops themselves that we can't draw using the standard interval. From the point of view of a T-Rex, you might say that the circle looks just like a line. Any loop that the T-Rex might draw will be contractible. The circle is just too big for the T-Rex to even notice that it loops around. You may be getting the feeling that homotopy theory is somewhat broken, at least when we consider such big spaces. How can we fix it? The answer lies in a variant of homotopy theory called big homotopy theory. The basic idea, starting with regular homotopy theory, is to systematically replace the standard interval, whenever it appears, by arbitrary big intervals. What we call a big interval here is a topological space obtained by equipping a totally ordered set with its ordered topology. For such a space to actually be a big interval, we also require that it be connected and compact. In that setting, connectedness boils down to the order being dense and complete, and compactness boils down to the order having both a minimum and a maximum. We will systematically denote these by 0i and 1i. Using the notion of big intervals, we can now define the notion of big paths from x to y, where x and y are points in the topological space X. This simply means a continuous map from any big interval I to x, mapping the minimum of I to the point x and the maximum of I to y. A big loop based at x is then simply a big path from x to itself. Equivalently, you can describe a big loop as a continuous map from a big circle to x, mapping a given point to the point x. We can already define interesting notions, like big path-connected spaces, a generalization of path-connected spaces, where we only require that points be joined by any big path, not necessarily a standard path. For example, big intervals are always big path-connected, basically by definition, but usually they are not path-connected. However, funnily, the space usually referred to as a long line is still path-connected, but barely. We have everything we need to define big homotopies. Given two big paths f and g, connecting the same 2 points x and y, we say that they are big homotopic when you can find the following. First, each of the big paths f and g has its own way of measuring time, namely the big intervals I1 and I2. So we need a single big interval I double bar that will, in some way, unify both, but may also allow paths longer than both f and g. We also need another big interval, the one I will call j double bar, in order to denote the time of the big homotopy itself. We need two order preserving surjections from I double bar to the big intervals I1 and I2, in order to relate the path time of the homotopy to the respective times of the path f and g. Finally, we need a continuous map H, the big homotopy itself, from the Cartesian product of I double bar and j double bar to x. That big homotopy must satisfy the following. At the beginning of the big homotopy, when the second argument equals the minimum of j double bar, we must recover the path f, or more precisely, f composed with the order preserving surjection p from I double bar to I1. Similarly, at the end of the big homotopy, we must recover the path j, composed with the order preserving surjection q from I double bar to I2. Moreover, at any given moment during the big homotopy, corresponding to any element of j double bar, the corresponding restricted map must be a big path from x to y, so specializing the first argument to the minimum and the maximum of I double bar must always give x and y respectively. In this way, we have a continuously varying big family of big paths from x to y, essentially connecting the big path f and g. Since there's a notion of concatenation of big intervals, we can assemble two big homotopy classes of big loops based at the same point x. The group axioms are easily checked. This leads to the definition of the main star of this video, the big fundamental group of x. As soon as the space is big path connected, that group is independent of the choice of base point, up to isomorphism. But wait, is it actually a group? In fact, it's not even clear that it's a set, because we are authorizing arbitrarily large big intervals. So we would like to find an actual set that contains at least one representative from each big homotopy class. And that's exactly the problem solved in that article by Keith Penrode, that this video is mostly plagiarizing. In that article, it is shown that for any space x there is a specific cardinal gamma of x, such that only the big intervals of cardinality at most equal to gamma of x actually matter for the computation of the big fundamental group. In other words, past a certain threshold, all big loops are big homotopic to a loop whose length is below that threshold. So we can just ignore big enough big loops. This explains why regular homotopy theory usually works just fine. This is what happens when gamma of x is small enough. Now that we have a definition of the big fundamental group, we can revisit the examples from the introduction. For the super tall cylinder, you can check that it's actually big path connected, and that its big fundamental group is trivial. Similarly, you can check that any big circle is big path connected, and that its big fundamental group is Z. So, everything works as we wanted. You might say that the T-Rex doesn't have short arms anymore. Now, its arms can get as far as needed. In that article by Cannon and Connor, which spawned the whole topic of big homotopy theory, another example is given. Namely, they define a generalization of the classical Hawaiian earrings, the big Hawaiian earrings, and they compute the big fundamental group of that space. They show that the big homotopy group of the big Hawaiian earrings is what they call a big free group, which is a kind of free group consisting of transfinitely long words. Even in this context, you might still find value in the regular, usual small fundamental group. You can use it to model situations where homotopies have constraints on their sizes without breaking the algebraic structure. If you put this kind of size constraints on homotopies and loops, usually you will break the algebraic structure. You won't get a fundamental group. Here, this is not the case, and this is all thanks to the ultrametric behavior of infinite cardinals. Thinking about these things actually made me realize that every topological space has metric properties baked in. You can define the distance between any two distinct points as the smallest cardinality of an infinite connected set that contains them both. You could also do this with the smallest cardinality of a big interval connecting them. In both cases, you obtain the map valued in cardinals that formally satisfies the axioms of a distance. It even satisfies the ultrametric inequality, so it looks like topological spaces do contain some information about size and not only about shape. This contradicts the way topology is often advertised. I hope you liked my presentation. In case you want to think more about big homotopy theory, you should read the source articles for this video. It's a very young topic, and a lot of very natural questions have not been studied yet. I have listed a few, basically trying to imitate some of the fundamental questions of homotopy theory. Think about them if you want, and see you next time!